Hi, I'm Raven Fernandez from EK31. I refer flexible antenna. So, what is flexible electronics? Flexible electronics, also known as flex circuits, is a technology for assembling electronic circuits by mounting electronic devices on flexible plastic substrates. Why we go for flexible antennas? The field of flexible antennas is witnessing an exponential growth due to the demand for wearable devices, Internet of Things framework, point-of-care devices, personalized medicine platform, 5G technology, wireless sensors network, and communication devices with a smaller form factor to name a few. The choice of non-rigid antennas is application-specific and depends on the type of substrate, materials used, processing techniques, antenna performance, and the surrounding environment. Material used for flexible antennas is polymer-based antennas, textile antennas, microfluidic antennas, carbon nanotube antennas. Question number 1. Blank, also known as flex circuit, is a technology for assembling electronic circuits by mounting electronic devices on flexible plastic substrates. A. Flexible antenna. B. Flexible electronics. C. Flexible person. D. Flexible plastic. The correct answer is letter B. Flexible electronics. Polymer-based antennas. Current advances in the electrical conductivity level of conducting polymers, or CP, and remarkable improvements in their stability are making these materials very striking potential alternatives to copper in planar antennas. This is mainly so in applications where lightweight, inexpensive, and conformal antennas are a consideration. There have been isolated efforts in the past towards using conducting polymers as materials for antenna and transmission line design. This chapter attempts to give a methodical investigation of key factors that are significant for understanding of these materials, their design and simulation as basis materials for building microwave antennas. The proposed conducting polymer-based antennas offers great mechanical flexibility and robustness, which indicate its promising potential for possible seamless integration in flexible electronics. Number 1. Silicon elastomers, or polydimethyl siloxane, or PDMS. So, recent option for PDMS, an expensive flexible polymer, can withstand mechanical strain, can be mixed and cured at room temperature. Dielectric properties can be tuned. Next. Number 2. PDMS ceramic composite. Polymer ceramic composites offer flexibility, low loss. The fabrication process of ceramic composite substrates. Number 1. Add ceramic powder to PDMS. Number 2. Mix under vacuum at high speed. Number 3. Pour in Petri dish and leave for 1 day. Number 4. Peel of the Petri dish. Figure number 2. Patch antenna made from PDMS ceramic composite. This is the picture of flexible patch antenna. So next. Question number 2. Which of the following materials that can be mixed and cured at room temperature? A. Ceramic composite. B. Silicon elastomer. C. Twisted liquid metal. D. All of the above. The correct answer is letter B. Silicon elastomers. Next. Textile antennas. Textile antennas are a special class of antennas that are partially or entirely made out of textile materials. In contrast to conventional antennas, which consist of rigid materials, the textile composing a textile antenna are divided into electrically conductive fabrics, denoted electrotextile and applied for the radiating and grounding parts, and dielectric materials for the insulating parts of the antenna, and can be intuitively understood the reason behind the use of textile materials in antennas lies in the application for which they are intended, being smart textile system and body-centric communication. Smart textile system represent a new concept of garments that, in addition to traditional functions such as protecting the body against the environment, also offer additional functionality such as sensing, actuating, and communication realized by wearable devices that integrated into the smart garment. Sensing functions are realized by sensors integrated into the textile garment's materials and are intended to detect the state of the wearer. Example: body temperature, heart rate, position, and or the state of the surrounding environment. Example: external temperature and humidity. Actuating functions are enabled by garments integrated actuators that provide signals and or alarms in order to inform, command, or warn the wearer about certain events regarding his or her state or the state of the surrounding environment. Finally, communication is realized in a wireless way by means of an integrated wearable textile antenna in combination with a wearable transceiver. Such a kind of wireless communication takes place between the human body and the surrounding environment and is also referred to as body-centric communication. In parallel with the textile antennas, this has become a very popular field of research over the last decade, with crucial importance for plenty of applications, ranging from monitoring of vital signs of patients to coordination and monitoring of rescue workers, but also in the entertainment sector and in sport. Patch antenna is a type of antenna with a low profile which can be mounted on a surface. It consists of a planar, rectangular, circular, triangular, or any geometrical sheet or patch of metal mounted over a larger sheet of metal called a ground plane. Next, question number 3 is a type of antenna with a low profile which can be mounted on a surface. Letter A, patch antenna. Letter B, substrate. Letter C, ground plane. Letter D, feed line. The correct answer is patch antenna. Next, microfluidic antennas. Liquid metals are filled in microfluidic cavities in a silicon elastomer. The liquid metal prevents loss of electrical connectivity when the antenna is deformed. Liquid metal antennas, on the other hand, can conform to any shape without strain and can be reversibly deformed. Next, question number 4. It is a liquid metal antenna that can conform to any shape without strain and can be reversibly deformed. A. Polymer-based antenna. B. Compressed nanotube. C. Textile antenna. D. Microfluidic antennas. The correct answer is letter D. Microfluidic antennas. Compressed nanotube. CNTs are well suited for virtually and application requiring high strength, durability, electrical conductivity, thermal conductivity, and lightweight properties compared to conventional materials. Currently, compressed nanotubes are mainly used as additive to synthetics based flexible antennas. Single compressed nanotube, ito yung tsura. And this is the cross-section. Applications. High-gain beam-forming antennas for wireless system. Next. What are the advantages of carbon nanotube? The unique nature of carbon combines with molecular perfection of single-wall compressed nanotube to endow them with extraordinary material properties, such as very high thermal and electrical conductivity, stiffness, strength, and toughness. Number 2. What are the disadvantages of carbon nanotube? One of the main disadvantages of carbon nanotube is the lack of solubility in aqueous media. And to overcome this problem, scientists have been modifying the surface of CN carbon nanotube. Example, fissionalization with different hydrophilic molecules and chemistries that improves the water solubility and biocompatibility of compressed nanotube. Various types of flexible antennas. Liquid metal planar inverted cone antenna or PICA. This is the sketch of its cable connection to the antenna. This is the ground plane, feed point, leaf-shaped radiator. The antenna is manufactured by injecting liquid metal into microstructure channel in the elastic PDMS materials. The antenna has a good return loss of 10 decibel in the operating frequency, and the radiation efficiency was also observed to be greater than 70%, which is considered good. The produced antenna allows stretching up to 40%. It is highly broadband antenna. The planar inverted cone antenna, or PICA, operates in the ultra-wideband, or UWB, of frequency 3.1 to 10.6 GHz. Question number 5. What is the minimum percentage allows antenna to stretching up? A. 40%, B. 75%, C. 50%, D. 100%. Letter A. 40%. Reversibly deformable and mechanical tunable fluidic antennas. The antenna consists of a fluid metal alloy with tactic gallium indium E-gain injected into microfluidic channels comprising silicon elastomer or PDMS. Fluidic dipole features withstand mechanical deformation or stretching, bending, rolling, and twisting. Resonant frequency can be tuned mechanically by elongating the antenna. Resonates at 196 MHz. Efficiency is around 90% or approximately at a board frequency range 1910 to 1990 MHz. The size of antenna is 54 mm. Simple to fabricate. Figure number 1, prototype antenna being stretched. Figure number 2, prototype antenna being rolled and antenna self-heals in response to sharp cuts. Next. Question number 6. What types of metal used in mechanical tunable fluidic antennas? A. Copper, B. Stainless, C. Alloy, D. Aluminum. The correct answer is letter C. Alloy. Elastic antennas by metallized elastomers. The objective of this is to investigate elastic antennas made by metallized elastomers at RF frequency for microwave transmission lines and antennas application. This is the figure 1 elastic coplanar waveguide. Figure number 2 normal coplanar waveguide. Figure number 3 ultra-wideband monopole antenna. Figure number 4 radiation pattern. Both give radiation pattern as expected for a normal monopole antenna. Figure number 5 simulated return loss of ultra-wideband antennas. A millimeter wave microstrip antenna array on ultra-flexible micromachine polydimethyl siloxane or PDMS polymer. The use of PDMS, an ultra-flexible polymer, as a substrate for the realization of reconfigurable microwave device in the 60 GHz band is presented. As bulk, PDMS is demonstrated to be lossy at millimeter waves. Membrane-supported devices are considered. A new reliable and robust technological process has been developed to micromachine membrane-supported transmission line and microstrip antenna arrays. It is shown that transmission line printed on 20 mm thick membranes exhibit similar performance as bulk substrates commonly used at millimeter wave frequency. A microstrip antenna array has been also designed and fabricated to demonstrate the feasibility of directive antennas supported by large membrane, promising applications for mechanical beam steering, beamforming, and frequency-tunable antennas are expected. Next. Design and manufacturing of stretchable high-frequency interconnects. The increasing number of biomedical applications for electronic systems have led to the need for stretchable electronics in order to significantly enhance the comfort of the user. This paper described the design and manufacturing process of new stretchable high-frequency interconnects with meander-shaped conductors in a coplanar waveguide topology. The novel interconnects are produced based on laser ablation of a copper foil, which is then embedded in a highly stretchable, biocompatible silicon materials. Measurements on prototypes of the designed stretchable high-frequency interconnect revealed a maximal magnitude of negative 14 dB for the reflection coefficient and a minimal magnitude of negative 4 dB for the transmission coefficient in the frequency band up to 3 GHz. The influence of stretch on the performance of the high-frequency interconnect was analyzed using a stretch testing machine. The results showed that nor the magnitude, neither the phase of the transmission coefficient was influenced by elongation up to 20%. Next. What future holds for these antennas? Flexible RFID tags, e-textile, military, medicine, and airplanes. That's all. Thank you po, sir. And the presentation.